Welcome everyone. My name is Satvik Singh. I am a master's student at the Indian Institute of Science, Education and Research in Mohali. And today I will be speaking about my recent work with Dr. Ayan Nichita from LPT Toulouse. This was performed as part of my summer project in 2020. The paper has recently been uploaded on the archive. This is the archive identifier for those of you who are interested. So the paper, as the title suggests, talks about the PPT-squared conjecture, and in particular, we show that this conjecture holds for a special class of maps known as the Choi-type maps. So before beginning with the presentation, let me just take a moment to thank the organizers of the Asian Quantum Information Science Conference for giving me the opportunity to present my work at this wonderful conference. So let me just begin by describing the outline of this talk. So I will begin with some motivation on the conjecture of the on the PPT squared conjecture, and then these three sections will form the core of this presentation. And finally, I will conclude the presentation by giving some directions for future research on this topic. So for the motivation, let me just state the conjecture itself. So the PPT squared conjecture, it was first proposed by M. Christanel in 2012. The conjecture talks about linear maps between matrix algebras, and in particular about PPT linear maps. So these are the maps which are completely positive and completely co-positive at the same time. And for these maps, the conjecture says that their composition with themselves result in entanglement breaking maps, meaning that the partial action of this composition on any bipartite state results in a separable state. So that is the definition of the entanglement breaking property for maps. Using the Choi-Koisky isomorphism, the statement can be translated in terms of bipartite matrices. So in that language, the statement, the conjecture says that for any two arbitrary bipartite matrices or states, rho AC and rho CB, and for any arbitrary bipartite positive operator M, this big expression corresponds to a separable state. So the way to think about this is that if let's say Alice and Charlie, they share this PPT state rho AC, and Charlie shares another PPT state rho CB with Bob, then the resulting state on Alice's and Bob's subsystem, uh, conditioned on any measurement by Charlie, is separable. So that is the statement of the conjecture. So this can be thought of as a generalized swapping procedures, and so basically the statement says that swapping of entanglement between any two bipartite PPT state results in a separable state. So this has profound implications in the realm of cryptography, particularly in the realm of key distribution protocols, where this entanglement swapping between two states is a key ingredient. So in those situations, the conjecture implies that PPT states cannot be used as a resource. So let me now talk about the kind of maps that we consider in our work. So these are the uh, maps which are covariant under the action of the diagonal unitary group, meaning that for all diagonal unitaries U and matrices X, this phi of U x U star is equal to U star phi x U. So you can push these diagonal unitary matrices out from the brackets, and this conjugation with this conjugation sign, which is basically the matrix adjoint. And in terms of Choi matrix of the map, this covariance condition translates into this invariance condition. This is a local invariance condition, and this can be equivalently used to define the class of DUC maps. And this other class of conjugate diagonal unitary covariant maps, the definition is almost identical except for this conjugation. This is not present here. So it turns out that these classes of maps, they admit neat parameterization in terms of these matrix pairs. So these A and B, they are arbitrary complex matrices with equal diagonals. And using these matrices, the action of these maps can be um, described in this fashion. So the first part is just a diagonal mixing operation. It takes the diagonal of the matrix and then mixes it according to this A matrix. And then the resulting vector is then again put in the form of a diagonal matrix. And the second part is the off diagonal. Second part basically is just this entry-wise product between this B tilde matrix and X or X transposition, depending upon which class of matrix, which class of maps we are looking at. And this B tilde is basically the same matrix as B, but with zero diagonal. And that is why this is the off diagonal part of the action. And so in this, when we describe the action of these maps in this form, it becomes clear that the classic Choi map on the three-dimensional matrix algebra, this is actually a CDUC map with A and B matrices defined as follows. So it also this class of maps is actually quite rich, and there are many other examples of classes of maps which are DUC and CDUC. So the upshot of this parameterization is that many different properties of these maps can be translated in terms of some constraints on the associated matrices. In particular, the PPT and entanglement breaking property can be described in terms of certain these constraints on the corresponding matrix pairs. So this the symbol, this curly inequality sign, this represents entry-wise non-negativity of A, and this normal inequality sign, this is for positive semi-definiteness. So note here that the entanglement breaking property, this corresponds to pairwise complete positivity of the matrix pair AB. Basically, that amounts to saying that there exists certain vectors V and W, a finite set of vectors such that this pair AB can be decomposed in this fashion. So that is the definition of pairwise complete positivity of a matrix pair. And from the definition, it is clear that this A matrix it is entry-wise non-negative, and the B matrix is positive semi-definite, right? Because the conjugation, the entry-wise product of a vector with its complex conjugate gives a non-negative vector. And similarly, this B matrix, this is just a sum of Frank-1 projections on these vectors. So this is positive semi-definite. And these entry-wise inequalities between the entries of A and B, they can also be easily deduced from this definition. And so these are basically the necessary conditions for membership in this cone of PCP matrix pairs. But it should be noted that these are not sufficient because I mean there exist maps, CDUC maps, which are PPT but not entanglement breaking. So let me now talk about the primary technical tool that will be used in the proof of our main result later. This is the notion of factor width. So let me begin by defining it for a single matrix B. So for a positive semi-definite matrix B, we say that it has factor width k if it admits a decomposition, a rank 1 decomposition with vectors Vn, where Vn are such that the size of the support of each of these Vn is less than or equal to k. So this represents the size of the support of the vector. And if each of these sizes is less than or equal to k, we say that the matrix has factor width k. And similarly, for the pairwise completely positive matrices, we say that it has factor width k if it admits a decomposition with vectors v and w, a finite set of vectors, such that now instead of the individual sizes of the supports, we look at the common support of these v and w vectors together. So the size of the intersection of the two supports of these two vectors should be less than or equal to k for each n. And if that is the case, then the matrix pair is said to have factor width k. So from the definition, it is immediately, it is evident that these sequences of inclusions hold. So these factor width k subcones can be thought of as providing inner approximations to this big cone of PCD, PSD and PCP matrices and matrix pairs respectively. So for our purposes, we will um, employ this characterization of factor with two subcones. So before talking about this characterization, let me begin. Let me just define this notion of comparison matrix. For any complex matrix, its comparison matrix is defined entry-wise in this fashion. So diagonal is just the absolute part of the matrix, and the off-diagonal part is the absolute value, but with the sign inverted, right? So with this definition, the we can actually provide a nice characterization of this subcone of factor width two positive semi-definite matrices. And the result is that a matrix A is positive semi-definite with factor width 2 if and only if the corresponding comparison matrix is positive semi-definite. So this gives us a very nice and easily verifiable condition for membership in this factor width 2 cone. And this is an if and only if statement. So this is a complete characterization for this subcone. And using this characterization, we can obtain a similar one for the factor width 2 PCP cone. So assumption here is that the matrix pair that we are considering, it already satisfies the necessary conditions that we earlier talked about um, for membership in the PCP cone. So if the matrix pair satisfies these necessary conditions, and in addition, if the B matrix has factor width 2 when considered as a positive semi-definite matrix, then the pair has factor width 2 as a PCP pair, right? And so this can actually be thought of as providing a very nice sufficient condition for membership in this PCP2 cone, which is a subcone of the PCP cone. So in terms of linear maps, if this B matrix is such that it has factor width 2, or equivalently is such that the comparison matrix is positive semi-definite, then the corresponding linear map DUC or CDUC, it is guaranteed to be entanglement breaking. So this is basically, this gives us a very nice sufficient condition for membership in the PCP cone, and equivalently for guaranteeing the entanglement breaking property of the corresponding DUC and CDUC maps. So now we move on to the main result of our paper, and we will use this characterization in the proof of this result. So the result is basically that the composition of any two arbitrary PPT DUC or CDUC maps is entanglement breaking. So the first step here is just to derive the composition rule itself. So I will just, for the purposes of this talk, I will just talk about the case where the two maps getting composed are of the same class. And in that case, the resulting map is guaranteed to be CDUC, and the associated pair, uh, this calligraphic A and B, it is of this form. So the calligraphic A is just the matrix product of A and C, and the calligraphic B matrix is just the entry-wise product of B and D. But then we have to make the diagonals same, so we add the diagonal part of AC and then subtract the diagonal part of this B shoe product with D. So this is the composition rule, and notice that since the maps being composed are PPT, the composition is also guaranteed to be PPT. And this implies that the calligraphic A and B matrices, they satisfy these necessary conditions for membership in the PCP code, right? Because they correspond precisely to the PPT condition for the corresponding linear maps. So this means that we can apply our previous result, this one, and to apply it, we just need to show that this calligraphic B matrix is actually um, um, has factor width 2 when considered as a positive semi-definite matrix, right? And so that is precisely what we do now. So it is instructive to look at the 3 cross 3 case first. So this is the matrix, and immediately it is clear that if we just collect these A11, C11, A22, C22, and A33, C33 in this first term, which is just the diagonal of the Schur product of A and C matrices, and the remaining terms can then nicely be arranged in this fashion. So these are, these matrices, all of them have support on the two-dimensional subspace of the three-dimensional matrix space, and each of these is positive semi-definite. Why? Because these entry-wise inequalities hold, right? Because these are precisely the conditions that ensure that the maps being composed together are PPT. And so these inequalities show that the determinant of these three matrices is non-negative, and also that since A and C are entry-wise non-negative, the diagonal is entry-wise non-negative, which implies that all these matrices are positive semi-definite. And this suffices to show that the calligraphic B has factor width 2, right? Because it can be split up as a sum of matrices which have support on a two-dimensional subspace. And this also holds for arbitrary D cross D case. This decomposition can be shown to hold for D cross D matrices as well, and this completes the proof of the result because we can immediately apply this characterization to deduce that the composition is PCP, or in other words, the corresponding linear map is entanglement breaking. So, which is precisely what we wanted to show. Now, let me just conclude by talking about some open problem regarding this conjecture. So, obviously, this conjecture is open for general maps, and in particular, there is this generalization of the maps that we considered in this paper. This is the class of diagonal orthogonal covariant maps, where instead of looking at diagonal unitaries, we now look at a diagonal orthogonal covariance condition, which is precisely this. And we can repeat the entire argument right from the beginning, right? We look at the parameterization of these maps in terms of matrix triples. Now we are looking at triples of matrices instead of pairs, and then you can describe the properties of these maps in terms of some constraints on the corresponding matrices. The entanglement breaking property is now described in terms of the triple-wise complete positivity of this matrix triple, which is a generalization of the pairwise completely positive cone of matrix pairs. And then if you want to talk about the PPT-squared conjecture, we would look at the composition of these maps. And again, it is by using elementary algebraic techniques, one can derive the composition rule for DOC maps. It is this big composition rule. And now the question is whether for arbitrary PPT DOC maps, the composition is entanglement breaking or not, meaning that if A, B, and C, A1, B1, C1, and A2, B2, C2 correspond to DOC maps, PPT DOC maps, in the sense that the ABC matrices, they satisfy these constraints. I'm sorry. Then if we compose it in this fashion, the question is whether the composition, this calligraphic ABC, this triple is triple wise completely positive or not, and that is an open question as of now. But we conjecture that this question can be answered in the positive, meaning that the PPT squared conjecture would hold for DOC maps as well, but we have not been able to prove it as of now. So at this point, let me just quickly mention that this notion of factor width can also be, defined for TCP matrices, but this characterization for the factor width 2 cone would not work for TCP matrices, and there exist counterexamples to show that this will not work. So that is partly why the question of the validity of the PPT squared conjecture is a bit tricky for DOC maps. All right, so I guess with this I should conclude my presentation, and these are some of the references that were used in this talk. If you have any further questions regarding this, please feel free to contact me. You can get hold of my email from this archive posting that is there on the internet. All right, thank you. Thanks a lot for your attention. Um,